Good morning. So myself, Dr. Maheswara Rao, Department of Civil Engineering, Institute of Aeronautical Engineering. Our course name is Fluid Mechanics. Our today's topic is Hydrostatic Pressure and Forces. Yeah. So what is the meaning of hydrostatic pressure? So if any water is there, example is, so if any object is inside the water, then this fluid will apply a force on this object. So, and the fluid is at rest. So, the pressure exerted by the fluid which is at rest onto the object which is inside the fluid, that is called the hydrostatic pressure. Okay, if you multiply that into area of that object, so the force will get. The course outcomes. So that means after completion of the course, what the students can know, can solve. Okay. So here, that is the course outcomes. Course outcome 1 is the students will be able to define the fluids. So what is the fluid and what are their properties and what is the surface tension, and all these things will come under the course outcome 1. And course outcome 2 is the Newton's law of viscosity. So here classification of fluids based on the Newton's law of viscosity. That means if any fluid obeys the Newton's law of viscosity, those are called Newtonian fluids. If any fluid will not obey the Newton's law of viscosity, then those are called non-Newtonian fluids. So like that, classification of fluids and some problems on the Newton's law of viscosity will come under the course outcome 2. Course outcome 3. So here it is a capillary rise or fall. So that means when any fluid is there, if we insert a small diameter pipe, so some fluids will rise its level. So it is normal level. So if you insert pipe, it will rise here. So that is called a capillary rise. And some other fluids, if you insert small diameter pipe, its level will lower to fall. Okay. So that is called capillary fall. That will come under the course outcome 3. So course outcome 4 is the surface tension. That means any fluid at its surface, it is having some tension. So which is called surface tension. That is under course outcome 4. And course outcome 5 is the compressibility. So if you take a gas, so if you apply any external forces over it, so it will become smaller volume. So if volume changes, then those fluids are called compressible fluids. If some water is there, so if you apply external force, so its volume will not change. So if volume is not changing, those are called incompressible fluids. So example for the compressible fluids is the gas, and example for the incompressible fluid is the water. This is the water. So the course outcome 5, you get knowledge of this compressibility and capillary. And course outcome 6, it is nothing but the pipe flow. So that means in a pipe, so if any fluid is flowing, then there will be friction between the pipe surface and the fluid. So those are called fluid friction. So there will be loss in the energy due to these frictional forces. Okay. So and hence energy lost also will occur if it travels from one point to another point. So this pipe flow or fluid friction or loss of energy, this will come under the course outcome 6. Today's topic is hydrostatic pressure and forces. Hydrostatic pressure means what? So it is the pressure given, applied by the fluid onto the object which is inside the fluid, and fluid is also at rest. Okay, that is the static. Hydrostatic. Static means no movement. So that means fluid is at rest. Hydro means water. Static means without movement. That means fluid is at rest. So then the pressure, how much pressure will be applied onto the object which is inside the fluid. If we see the definition, so hydrostatic pressure is the pressure exerted by a fluid at equilibrium. So it is nothing but at the equilibrium, the fluid will exert some pressure. Okay, due to why it is giving for pressure means because of the force of gravity. So its gravitation power will act so that the water will exert some pressure depending upon the depth from the surface of that fluid. So if the fluid is here, so if any object is here, there is no pressure at all by means of this fluid. So if some object is there at a depth of here h, then the force will be exerted by the fluid onto the object. So that is equal to rho g h, where rho is the density of fluid, g is the acceleration due to gravity, and h is the depth of that particular object from the surface of the fluid. Okay, so it increases with depth. So if the object is here, so it will have somewhat lesser pressure. If it is having so deeper, that means this if it has h increases, because density is constant, acceleration due is constant. As depth increases, the pressure also will increase. So that is the hydrostatic pressure. So we can see here, it is a liquid or water surface. So it is one object. So the object may be a sheet, a surface. It is an zero thickness. That means it is a sheet. Okay. The sheet can be in vertical position or horizontal position or even inclined position. So hydrostatic pressure will be different depending upon the position of the surface. So if it is vertical or if it is horizontal, if it is inclined, it will have different pressures. So you can see in this figure, so it is an inclined surface. You see, rotated view, you can see like this surface. This is the area of that object. This is the film or surface of that particular object. So where it will be utilized, we can see here. So if it think it is a tank, here is one gate is there. Example. So how much pressure will be applied onto the gate because of the water pressure. And here also inclined gate is there. So how much pressure is applied by means of this fluid at rest. So here important considerations: depth variation, fluid density, surface shape. So three things are there. Depth variation. So what is telling? Hydrostatic pressure increases linearly. So as depth is increased, so the pressure is also increased linearly. Because the formula is here, rho g h. So rho is constant, g is constant. As h increases, pressure is also increases. It is linearly varied. So depth variation is linear variation. So if depth is varying, pressure is also varying. That means if depth is increasing, pressure is also increased. So on a submerged surface means if any water is there inside of that fluid, some object, if it is there, that is called a submerged surface. Then fluid density. So if it is water, it will have some 1000 kg per meter cube. Some other fluid will have some other density. So what will happen? Change in the fluid density will affect the magnitude of hydrostatic pressure. So depending upon the density of the fluid in which the surface is submerged, so the pressure also will be related to that. If density is more, pressure also will be more. As depth is more, pressure is more. As density is more, fluid density, so the pressure is also will become more. And surface shape. So irregular surfaces require integration to the distribution to the total force. If it is a rectangular surface, that means if it is here one surface is there, okay, so L into B. So we can multiply L into B is the area. So pressure into area will get the force here. If it is circular, so pi r square, we will get the area of the circular surface. So that area will be multiplied with the pressure, so that we will get the pressure force. Okay, hydrostatic force. Here hydrostatic pressure is there, hydrostatic force also there. Pressure means it is in Newton per meter square, like that. So if you multiply with any area of that particular surface, you will get the force. Okay, so that is the surface. If the surface is irregular, so it is not a circular shape, okay, it is not a rectangular shape, then there will not be any standard formula for that. So if it is circular, pi r square is the formula, and if it is a rectangle, length into width is the formula for the surface area. But if it is any surface which is irregular in shape, so how will you calculate the area of that particular surface? By using this integration. So mathematics integration, by utilizing the integration, we can get the area of that particular irregular surface. So after getting that, if you multiply with the pressure, hydrostatic pressure, you will get the hydrostatic force on to the particular irregular surface. And practical applications. So where will it be placed? Why should we learn the pressure, how much pressure is applied onto a submerged surface? Already fluid is there and some object is there, the surface. How much pressure is applied? How should you know? How should we calculate? How should you know all these things? Means it is having some practical applications. Design of dams. Okay. Dam is what? Dam is nothing but the obstruction from the flow of water. So if the water is there, it will be stopped by constructing dam. This is a dam. Okay. So unless you calculate the forces due to water, hydrostatic forces, then only we can design the dams. So if you don't design it properly, then if the pressure force is more, then overturning will take place or damage of that particular dam will occur. So in order to design properly, we must know the force applied by the fluid onto the dam. We have to know initially. That's why this hydrostatic pressure is the application of the in case of design of dams. And submarines. Okay, submarines means it is nothing but the traveling below the water surface. So that is a thing that will travel below the water surface. So that also, if submarine is here, they will also exert some water pressure, okay, depending upon the depth of that particular submarine. So if it is submarine is going deeper and deeper into the ocean, the pressure will become more and more. So if it is designed for a particular pressure, that submarine, if you allow them to go deeper and deeper into the ocean, what will happen? The submarine will fail, will damage. So that's why before going to design of that submarine, we have to know the depth at which it will travel. So that we have to know. So then only we can design the submarine. So this is the another application of the hydrostatic pressures. And tanks and reservoirs. So what is the tank means? Overhead tank may be there. So overhead tank may be there or underground tank also there. It is a ground level. So below it, some water tank, underground tank. So overhead tank, OH, overhead tank, OHT, underground tank. So both are the water tanks. So these also will be given force by the water. So if you store the water in the underground water tank or as well as overhead tank, so then water will exert pressure on the surface of the walls of these tanks. So you want to safeguard this tank walls, so you have to design such that it can resist the hydrostatic pressure because of this existing water inside the tanks. So that is the another application. So it may be tank design or reservoir design. So this hydrostatic pressure knowledge is a must here. So the practical applications of these hydrostatic forces are to design the dams, to design the submarines, to design the tanks and reservoirs. And there is a formula, hydrostatic pressure is equal to rho GH. So here P is the pressure due to the fluid, rho is the density of the fluid, and G the acceleration due to gravity, and H is the depth at which object is there below the surface of that. So if it is a surface, if it is an object, so this is the H. Okay. So you see here where P is equal to hydrostatic pressure in pascals or Newton per meter square. Pascal is nothing but the Newton per meter square. Rho is the density of the fluid in terms of kg per meter cube. H is the G is the acceleration due to gravity, 9.81 meter per second square, and H is the depth below the fluid surface. That means this is the H point, so below the surface. So this is the fluid surface. So this is the fluid surface. H is the depth, the object below the fluid surface. If you see the one small example for this. So water density, rho of water is nothing but constant. It is a 1000 kg per meter cube. That means if you fill the water in a box of 1 meter width, 1 meter length and 1 meter height. Okay. So then the weight of that particular water, this is 1 meter, 1 meter, 1 meter. Length, width, depth all are 1 meter. And if you fill up that box with water, it weighs 1000 kgs. Okay. So at a depth of 5 meters. What is this 5 meters? It is nothing but the H value. So you can see in this figure. So density of fluid is 1000 kg per meter cube. And depth is 5 meters. So what is the pressure? So pressure formula is rho G H. So rho is the 1000 kg per meter cube. G is the acceleration due to gravity 9.81. H is the 5 meters. So if you multiply this rho GH, you will get the pressure due to the fluid at a depth of 5 meters is equal to 49,050 pascals or 49,050 Newton per meter square. Then hydrostatic force here. So till now we have done here is the pressure. So P is the rho GH is the formula. It is a pressure. Now it is a force. How will you get the force? So just multiplying this pressure into area. So this is the area. Capital A is the area of the object. So if the pressure is multiplied with the area, so you get the force, which is the hydrostatic force here. So here definition, if you see, hydrostatic force is the total force exerted by a fluid on a surface due to hydrostatic pressure. It is nothing but the total force exerted by a fluid onto the surface. So it is integral of pressure over the area of the surface in contact with the fluid. So the formula for the hydrostatic force is P average into area. So pressure average. So why it is average pressure means, so it will have some area. Okay. So at particular depth, so that means average depth will take, then that is called a average pressure. So F is the hydrostatic pressure newtons because the pressure is Newton per meter square. If you multiply with the meter square area, so Newton per meter square into meter square cancels, you will get the newtons here. So P average is the average hydrostatic pressure in terms of pascals. That means Newton per meter square. A, area of the surface in contact with the fluid. So that means if fluid is here, if some sheet is there, okay, thin sheet, so it is submerged surface. Okay, so area of this sheet, thin sheet, so that means length into width. So rectangular area is equal to length into width. So then you will get the area of that sheet or surface. If it is circular surface, formula is already square before like that. depending upon the shape of the surface, we can calculate the area of that surface, submerged surface. It may be regular shape like circular, rectangular like that, or it may be irregular shape, so that we can utilize the integration mathematics to get the area of that particular submerged surface. Then horizontal force acting on the submerged surface. If you see the definition here, horizontal force on submerged surface result from the pressure distribution in the fluid for vertical or inclined surface. So what is the meaning of this? If water is there, the surface can be in like this vertical position or horizontal position or even inclined position. Okay, the vertical or inclined surface, these forces can be calculated considering the pressure distribution at various depths. So then how will you calculate the pressure here? So here it is P average into area. So for a vertically submerged surface, hydrostatic force is equal to P average into area. So what does it mean? P average means here the water surface is here. This is the at H1 and this point is at H2 from the surface. So then average is H1 plus H2 by 2. So then you will get the average pressure. So and if you multiply with the area of that particular surface, so you will get the force, that means hydrostatic force acting on that particular submerged surface. So where Fh is the urgent hydrostatic force in newtons, P average is the hydrostatic pressure on the surface, pascals, A is the area of submerged surface in meter square. We see an example. So for a vertical rectangular surface, that means if water is there, the vertical surface is there, okay, vertical surface, then submerged water, height is 5 meters, this height is 5 meters here, width is 3 meters. Then what is the area of this surface? It is 5 into 3 is equal to 15 meters square. So depth at the bottom is 6 meters. This point is 6 meter from the top surface. So similarly, depth at the top is 1 meter. So here H1 is equal to 1 meter. Okay. H1 is equal to 1 meter. H2 is equal to 6 meters. The average height is equal to 1 plus 6 by 2 is equal to 3.5 meter. So here average pressure is equal to rho g h. So where is h is the average height. That means H1 plus H2 by 2. So rho is the density of water and g is the acceleration due to gravity, and H1 is 1 meter, H2 is the 6 meter divided by 2, you will get the average height of that particular surface, submerged surface. So if you multiply this, you will get the 39,240 pascals. And the area of the submerged surface is 5 meter by 3 meters. 5 meters is the height, 3 meters is the width. So if you multiply that, you will get the 15 meters square. So force, hydrostatic force is the hydrostatic pressure multiplied by the area of that particular surface. So you will get the 5,88,600 newtons. So you can see one more example. So here the vertical rectangle is also vertical. So that means water surface is here. Then this one is the vertical rectangular surface. Okay. So it is a rectangular surface. Height is 4 meters. So from here to here, it is 4 meter and width is 3 meters. So from here to here, it is 3 meter. Submerged in water. So it is water. Okay. It is a water. So our surface is submerged. Depth at the top, H1 is equal to 2 meters. So from surface, depth is equal to H1 is equal to 2 meters. Depth at the bottom, that means here, from the surface, from here, H2 is equal to how much it is? 6 meter. Okay. Then average height is equal to h1 plus h2 by 2. That means 2 plus 6 by 2. So that is 4 meters. So then average pressure, P average is equal to rho g h. So h is the average height. So rho is the density of fluid, water. G is the acceleration due to gravity. And h is the average h. H1 is from top it is 2 meters, from bottom it is 6 meters. So the average is 2 plus 6 by 2. You will get the average. So 1000, 9.81, 2 plus 6 by 2. So you will get the 39,000 pascals here. So then area of this, in order to find out the force on the submerged surface, force, it is a pressure. Now we are going to calculate the force. So pressure is multiplied with the area, surface area of that particular surface, you will get the force. So here the pressure is 39,000 pascals and area is 3 by 4. 3 meters is the width of the surface, 4 meters is the depth of the surface. Then if you multiply with 3 and 4, then we get the 12 meters square is the area of that particular submerged surface. Then force, hydrostatic force is equal to P average multiplied with the area of that submerged surface. So P average is equal to pressure average pressure is equal to 39,240 and the area of the submerged surface is 3 into 4, 12. Then you will get the 44,70,880 newtons. So if you review what we dealt today, okay. So here we dealt today is the hydrostatic pressure and force also. So the definition for the hydrostatic pressure is nothing but the pressure exerted by a fluid onto the submerged surface at equilibrium. That means the fluid is at rest. So the pressure will increase as the depth of the object or surface increases from the surface. Then these are the figures. So applicability is that if in a tank is having some gate at the bottom, maybe vertical gate or maybe inclined gate, how much pressure is applied by the fluid onto the particular gate. So that is one practical application. So here is a surface which is having a regular shape. Okay. So this regular shape area we can get by means of the integration methods. And here important considerations are depth variation. Okay. So depth variation means here if submerged surface is deeper and deeper and pressure also will become more and more. So as depth is increased from the submerged surface, from the top surface of the fluid, then pressure is also increased. It is directly proportional, and fluid density is also directly proportional. If the fluid density is more, then hydrostatic pressure is also will become more. So as depth increases, pressure increases. As fluid density increases, pressure increases. And surface. So for regular shapes of surface, submerged surface, you can get the area of the particular regular shapes like circular, rectangular, based on the formula pi r square, length into width like that. For a irregular shape, submerged surfaces, so you can get the area of that particular irregular submerged surface by means of the integration mathematics, using the mathematics. So if you see the practical application, so you must know this hydrostatic pressure, otherwise you cannot design the dams. Okay. So if you want to design the dams, that means how much hydrostatic force is applied onto the dam. So then only we can design the dam. Otherwise the dam will it will fail, it will break, okay, it will tilt. So many things will happen if it is not designed properly. And also submarines, so which is deep into the oceans. So if submarines also pressure will be applied by means of fluids. So if you don't design properly, the submarine hulls will break, so that it will fail. And also tanks and reservoirs. So underground tank is there, overhead tank is there. So whatever it may be, the tank's walls will be subjected to pressure, fluid pressure. So the tank wall should be strong such that it can withstand the hydrostatic force. So if you know how much force is applied onto the tank walls, then only we can design the thickness of that particular tank walls. So all these the practical applications like dams design, submarine design, and tank walls designs. And general formula for this hydrostatic for pressure is the rho GH, where rho P is the pressure and the hydrostatic pressure in Newton per meter square or pascals. Rho is the density of that fluid, kg per meter cube, and G is the acceleration due to gravity, 9.81 meter second square. H is the depth below the fluid surface. So any submerged surface which is at a depth of h from the fluid surface, that is the small h in terms of meters. So if you calculate if any object is there 5 meters below the surface of water, so that means if surface of water is this, if any object is here, it is depth of 5 meters. So then how much force will be applied? So by means of using the rho GH. Rho is the density of water, 1000 kg per meter cube. G is the 9.81 meter per second square. 5 is the depth of that particular object. So totally 49,000 pascals pressure will be applied onto the object which is at a depth of 5 meters below the water surface. And you can also calculate not only pressure but also force. So if you multiply this pressure with the area of that particular submerged surface, then you will get the force onto the submerged surface. So F is equal to P average into capital A, where A is equal to the area of the submerged surface. It may be rectangular or circular or regular in shape. So you can use the regular formulas, or even you can use the integration methods. So in order to get the area of that particular irregular submerged surface. So F is equal to hydrostatic force. P average is equal to the average hydrostatic pressure. Here A is equal to area of the surface in contact with the fluid. So here hydrostatic force P is equal to P average into area. So here Fh is the hydrostatic force, newtons. P average is the average pressure on the surface. A is equal to area of the submerged surface, meter square. So you can see one small problem here. Okay, so it is a rectangular surface. Width height is 5 meters, width is 3 meters. That means area is 5 into 3, 15 meters. The top is having 1 meter at a depth from the below surface, and bottom of the sheet, the surface is the 6 meters below the fluid surface. So then rho GH is the pressure, average pressure. So average means here H1 plus H2 by 2. That means surface fluid to the top of the submerged surface and bottom of the submerged surface. So that is 1 and 6 are given here. So then with the average 1 plus 6 by 2, then you will get the 13,000 pascals. So if you multiply the area of that submerged surface, which is 15 meters square, so you will get the 5,88 newtons. So it is another for problem, numerical example. Okay, so here also it is a rectangular in shape. What is given here, height is 4 meters, width is 3 meters. Then area of the submerged surface is 4 into 3, 12 meters square. And the depth, top of that submerged surface to the liquid surface, the water surface is H1 2 meters, and bottom of the submerged surface to the top of water surface is H2 is equal to 6 meters. Then average height is equal to H1 plus H2 by 2, that means 2 plus 6 by 2, 4 meters. So then P average pressure is equal to rho GH. So rho is equal to 1000 because it is water, 1000 kg per meter cube, and G is the 9.81 meter per second square. H1 plus H2 by 2 means 2 plus 6 by 2, that is average. You get the 39,000 pascals, and area of that particular surface is 3 by 4 into 12 meters square. So then if you multiply with the pressure into area of that particular submerged surface, you will get the force applied by the fluid onto the submerged surface. So references are K. Subramaniam, Theory and Applications of Fluid Mechanics, Tata McGraw-Hill Student 12, Modi PN and SM Seth, Hydraulics and Fluid Mechanics, standard book house design too. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.